Hello friends, welcome you all to the 46th lecture on functional analysis and its applications. In this lecture, we will discuss the self-adjoint operators. This is the content of today's lecture, self-adjoint operators. Definition of self-adjoint operators. A bounded linear operator T on a Hilbert space H is said to be self-adjoint if T star is equal to T. From this definition, we have the following simple properties. First, an operator T on H is self-adjoint, then inner product of Txy equal to inner product of x ty for every xy belonging to H. And conversely, means if inner product of Tx y equal to inner product of x ty, then T is self-adjoint. Second, for any T belonging to Bh, that is T is set of all bounded linear transformation on H, then T plus T star and T star T are self-adjoint. Explanation. By the property of self-adjoint operators, we have star of T plus T star. Okay. So we know that the property T1 plus T2 star equal to T1 star plus T2 star. Okay. So applying this property on this, we have T star plus star of T star, that is T double star. Also we know that T double star equal to T. So this term can be written as T star plus T. So we can write this first and then this, that is T plus T star. Therefore, star of T plus T star is equal to T plus T star. That is, as per the definition, T plus T star is self-adjoint. Also, star of T star T, we know that T1, T2 star equal to T2 star T1 star. Okay. So here star of T star T, then it will be T star into star of T star, that is T double star. Again, we use this property T double star is equal to T, that is we have T star T. So again, by the definition of self-adjoint operator, this is star of T star T is equal to T star T, that is T star T also self-adjoint. Hence, T plus T star and T star T are self-adjoint. Third property, the zero operator O and the identity operator are self-adjoint operators. Already we have proved O star is equal to O and I star is equal to I in previous lecture. Okay. So zero operator and identity operator also self-adjoint operators. Theorem. First, if An is a sequence of self-adjoint operators on Hilbert space H, and if sequence An converges to an operator A, then A is self-adjoint. Proof. Let An be sequence of self-adjoint operators and let An converges to A. Since each an is self-adjoint, we have an star is equal to an for all n belonging to n. To prove that A is self-adjoint, that is A is equal to A star. For this we prove that norm A minus A star is equal to 0. We know that norm x is equal to 0 if and only if x is equal to 0. So here if we prove norm A minus A star is equal to 0, that is A is equal to A star. Let us prove it. Now norm A minus A star can be written as norm of A minus An plus An minus An star plus An star minus A star. There is no change in this. Okay, we have added here An and subtracted An. Also added An star and subtracted An star. Okay, so by the triangle property of norm, we can write this less or equal to norm of A minus An plus norm of An minus An star plus norm of An star minus A star. Using An equal to An star. Okay. Here in the above and rewriting we get this one. Here common minus, so we can write this is norm of minus An minus A plus An minus An star, because An star is equal to An. Similarly this one also norm An minus A. Okay. This is also norm of An minus A, because norm alpha x equal to mod alpha norm x. So here alpha is minus 1, so mod minus 1, that is 1. So this can be written as norm An minus A, and this one 0. And we have this norm An minus A. Therefore, this equal to 2 into norm of An minus A. Hence, norm A minus A star less or equal to 2 into norm An minus A. And An converges to A, that is norm An minus A tend to 0 as n tend to infinity. Therefore, norm A minus A star is equal to 0. Therefore, A minus A star is equal to 0, which gives A is equal to A star. This proves that A is self-adjoint operator. Next theorem. Let S be the set of all self-adjoint operators in BH. Then S is closed linear subspace of BH, and therefore S is real Banach space containing the identity transformation. Proof. First note that S is non-empty. Since O is self-adjoint operator by the above property third, this one, so S is non-empty. If A1, A2 belonging to S, we prove that alpha A1 plus beta A2 belonging to S, where alpha and beta are scalars. Since A1 and A2 belonging to set S, that is belonging to set of all self-adjoint operators in BH. Therefore, A1 star is equal to A1 and A2 star is equal to A2. Noting alpha beta be real, then we have star of alpha A1 plus beta A2 equal to alpha bar A1 star plus beta bar A2 star equal to alpha A1 plus beta A2. Why? We know that T1 plus T2 star is equal to T1 star plus T2 star. So this can be written as alpha A1 star plus beta A2 star. Okay, and also know that alpha T star is equal to alpha bar T star. Okay, so this can be written as this one and this is this one. Okay, and alpha beta be real, then alpha bar is alpha and beta bar is beta. So we have alpha A1 plus beta A2. So here alpha A1 plus beta A2 star is equal to alpha A1 plus beta A2. Therefore, alpha A1 plus beta A2 is self-adjoint operator. Okay. Thus, A1, A2 belonging to S, this implies that alpha A1 plus beta A2 belonging to S. Hence, S is real linear subspace of H. Now, show that S is closed. To show that S is closed, let A be any limit point of S. Then there exists a sequence of operators An in S such that An converges to A as n tends to infinity. We have to prove A belonging to S, that is A is equal to A star. For this, let us consider as above, norm A minus A star can be written as norm of A minus An plus An minus A star. That is no change if we add and subtract An. Okay. Now applying the triangle property of norm, then this one less or equal to norm A minus An plus norm An minus A star. Again, as this can be adjusted as this one by adding An star and subtracting An star. Okay. So this can be written as norm A minus An as it is, and this one plus norm An minus An star plus An star minus A star. Again applying the triangle property of norm on this, we have less or equal to norm A minus An plus norm An minus An star plus norm An star minus A star. Okay. Since An belonging to S, this implies that An star is equal to An, that is self-adjoint. So this can be written as minus common. So norm minus An minus A plus norm An minus An plus norm An minus A star. Okay. Again applying this property, T1 plus T2 star is equal to T1 star plus T2 star. So by this property, this can be written as star of An minus A. Okay. So here this can be written as mod minus 1 into norm An minus A plus norm An minus An, and this one norm An minus A. Okay. Why? because norm of T star is equal to norm T. Okay, so this can be written as norm an minus a, and here an star is equal to an, that is an minus an, that is norm of zero operator, this one, and this can be written as mod minus 1 into norm an minus a, that is, so norm of zero operator, that is 0. Okay, hence norm of a minus a star less or equal to 2 into norm of an minus a. Here an converges to a, so this tend to 0 as n tend to a. Therefore, norm of a minus a star equal to 0. This implies that a minus a star is equal to 0 operator, that is a is equal to a star. This implies that a is self-adjoint, implies that a belonging to S. Thus, S is a closed. Since S is closed linear subspace of the Banach space BH, therefore S is also a complete space. Hence, S is real Banach space. Also, I star is equal to I. This implies that I belonging to S. This completes the proof of theorem. Next theorem. If A1 and A2 are self-adjoint operators on H, then their product A1, A2 is self-adjoint if and only if they commute. That is, A1, A2 is equal to A2, A1. Proof. Let A1, A2 be two self-adjoint operators on H. Okay, it is given. Then A1 star is equal to A1 and A2 star is equal to A2. First, we suppose that A1, A2 commute. Okay, this. That is A1, A2 is equal to A2, A1. Then to prove A1, A2 is self-adjoint. Now, star of A1, A2 equal to A2 star, A1 star. Okay, by the property, this T1, T2 star is equal to T2 star, T1 star. Okay, so by this property, star of A1, A2 equal to A2 star, A1 star. And here A1 star and A2 star with self-adjoint operator. Then A2 star, that is A2, and A1 star, that is A1. Okay. So here A1, A2 commute. So we can write this is A2, A1 is equal to A1, A2. Okay. So here star of A1, A2 is equal to A1, A2. So by the property of T star is equal to T, that is T is self-adjoint. So we can say that here A1, A2 is self-adjoint. Conversely, suppose that A1, A2 is self-adjoint. Then we have star of A1, A2 equal to A1, A2 by the definition of self-adjoint. This implies that A2 star, A1 star. Okay. It will be 1 and 2. So A1, A2 are self-adjoint. So this can be written as A2, A1 equal to A1, A2. Okay. This shows that A1 and A2 commute. Next theorem. If T is an arbitrary operator on Hilbert space H, then T is equal to O, that is zero operator. If and only if inner product of t x y equal to 0 for all x y belonging to H. Proof. Let t is equal to O, that is 0 operator. Then for all x and y, inner product of t x y equal to inner product of O x and y. And Ox, that is 0. So this inner product is inner product of 0 y, that is 0. Conversely, let inner product of t x y equal to 0 for all x y belonging to H. Okay, taking y is equal to tx, we get inner product of tx is equal to 0 for all x belonging to H. This implies that tx is equal to 0. So tx is equal to 0, that is t is 0 operator. Hence t is equal to O, that is 0 operator on H. Next theorem. If t is an operator on a Hilbert space H, then inner product of txx is equal to 0 for all x belonging to H if and only if t is equal to 0. Okay. So similar to above theorem, here inner product of txy is equal to 0 and here inner product of txx is equal to 0. Proof. Let t is equal to O, that is 0 operator. Then for all x belonging to H, we have inner product of txx equal to inner product of Ox x equal to inner product of 0 and x, that is 0. Conversely, let inner product of txx is equal to 0 for every x belonging to H to prove that t is 0 operator on H. Let x, y belonging to H, alpha, beta be any scalars. Then we have inner product of t alpha x plus beta y and alpha x plus beta y. Since t is linear, so this can be written as inner product of alpha tx plus beta ty and alpha x plus beta y. Using the property of inner product, this can be written as inner product of alpha tx and alpha x plus inner product of alpha tx and beta y plus inner product of beta ty and alpha x plus inner product of beta ty and beta y. So we have this one. Again, applying the property of inner product, this inner product of alpha x beta y equal to alpha beta bar into inner product of x y. So using this property, this can be written as alpha bar into inner product of tx and x. Similarly, this one alpha into beta bar into inner product of tx and y, and this plus beta alpha bar into inner product of ty x, and this one plus beta bar into inner product of ty and y. So this can be written as mod alpha square into inner product of txx plus alpha beta bar into inner product of txy plus beta alpha bar into inner product of tyx plus mod beta square into inner product of tyy. Okay. So this can be written as inner product of t alpha x plus beta y and alpha x plus beta y minus mod alpha square into inner product of txx minus mod beta square into inner product of tyy equal to alpha beta bar into inner product of txy plus beta alpha bar into inner product of tyx. Since inner product of txx is equal to 0, it is given. Okay. So left hand side each term as inner product of txx. So left hand side is 0. So from 2 we have alpha beta bar into inner product of tx and y plus beta alpha bar into inner product of ty x is equal to 0 for all alpha beta and xy belonging to h. When alpha is equal to 1 and beta is equal to 1, then equation 3 is inner product of txy plus inner product of tyx is equal to 0. Okay. If alpha is equal to I and beta is equal to 1, then I into inner product of txy minus I into inner product of tyx is equal to 0. Because here alpha is equal to I, beta is equal to 1. So this one, and here beta 1 alpha I. So alpha I bar, that is I bar is minus I. So multiplying 4 by I and adding to equation 5, we get 2I into inner product of txy equal to 0 for every xy belonging to h. Since 2I not equal to 0, taking y is equal to tx, we have inner product of tx and tx is equal to 0. So inner product of tx is equal to 0, that is tx is equal to 0. Tx is equal to 0, that is t is 0 operator. So this proves that t is equal to 0 operator. Next theorem. An operator T on a Hilbert space H is self-adjoint if and only if inner product of T, x and x is real for all x. Proof. Let us assume that T is self-adjoint operator on H. That is T is equal to T star. Then for every x belonging to H we have inner product of Tx and x can be written as inner product of x and T star x as per the definition of adjoint operator. Okay, so here T is self-adjoint, so this can be written as inner product of x and Tx. So if we change the points of the inner product, that is conjugate complex. So this can be written as inner product of Txx bar. That is conjugate complex of the inner product of Tx and x. So we know that Z is equal to Z bar. That is Z is real. So here inner product of Txx is equal to conjugate complex of the inner product of Txx. That is inner product of Txx is real. Conversely, suppose that inner product of Txx is real for all x belonging to H, then to prove T is self-adjoint. Since inner product of Txx is real for all x belonging to H, we have inner product of Txx is equal to conjugate complex of the inner product of Txx. So as per the definition of adjoint operator, inner product of Txx can be written as inner product of X and T star X and conjugate complex as this. Again, if we change the position, so we can double bar of inner product of T star X and X, that is inner product of T star X, X. Okay, so this can be written as okay. So this can be written as inner product of T star X, X. So this is equal to this. So it can be written as inner product of Txx minus inner product of T star Xx is equal to 0. So as per the additive property of inner product, this can be written as inner product of Tx minus T star Xx is equal to 0. That is, this can be written as inner product of T minus T star Xx is equal to 0. And above we prove if inner product of Txx is equal to 0, this implies that T is equal to 0. So this one is T minus T star is 0 operator. That is T is equal to T star. Therefore, the operator T is self-adjoint. In this lecture, we have discussed the self-adjoint operators and related theorems. These are the references which have been used in this lecture. Function analysis, Dover publications, written by George Beckman and Lawrence Naresi. Second, introductory function analysis with applications, John Whaley and Sons, written by Erwin Krejcik. Third, function analysis, New Age International Publishers, written by B.V. Limier. And fourth, function analysis, Tata McGraw-Hill, written by Walter Rudin. Thank you.